Today, on Xenodon, I have a new modification of which to show you guys. And that's a modification I call the Shunt Mod, which can be done on the drivers that are found inside of these cheap 405nm violet laser pointers that are often found on eBay. But before that, a little public service announcement and pre-criticism montage. That big bar is actually infrared in the 808nm range. Now, this light is not only dangerous because of its output power, but because you don't see it very well. So if it does get into your eyes, you won't blink, and this will cause prolonged damage because you won't react to it. That is a lot of infrared energy. As I said, one of the most dangerous lasers to look at. You can see just how much of that infrared radiation is coming out of that laser head. That's quite a lot. And that's quite damaging to the eyes as well. With that out of the way, let's talk about perceived dangers. And one of the biggest perceived dangers is that the cheap green laser pointers sold on eBay do not contain an infrared filter on them. Well, how big of a danger is this in reality? To help with this, I have a laser power meter here, and the readout is as follows. This column right here is in watts, the center is hundreds of milliwatts, and the far right one is in tens of milliwatts. So if I take the grass green laser pointer, which I reviewed in an earlier video, and hit the laser power meter with it, we can see that it pretty much does nothing, which means that it's under the 10 milliwatt range. Now, to show you that this does pick up infrared, I have one of my modified green laser pointers, of which I removed the monolithic crystalline assembly. This is the piece that contains the pump crystal, and it contains the frequency doubling crystal. If I hit the laser power meter, we can see that it comes up to about 300 milliwatts. I have a piece of dichroic glass here, and this will serve later on as a filter for blocking out most of the green coming off of a cheap green laser pointer module. You can see that for the most part, it doesn't affect the infrared going through, so it makes for a great demonstration assistant. Now let's test the power coming from a cheap 532nm laser pointer module. It's about 40 milliwatts, which is already above the safe limit, 5 milliwatts. To see how much infrared is actually coming through, I'm going to replace this dichroic piece of glass in the front, which will serve as a green laser light filter, and we can get a good look at the infrared coming through. To help with seeing the infrared light coming off of the laser pointer module, I have another one of my modified camera phones, and sure enough, there is in fact infrared light coming through. Well, how much infrared light? Under 10 milliwatts. Not too dangerous. Here's another aspect of which often isn't considered while talking about the dangers of infrared laser light, and that is the actual interaction of infrared light with human cells. To help explain this, I have my wallet, which is a dark black material, and I have my skin, which is filled with red blood material. I have my high-powered red laser pointer, which has been fixed since the last video, and I want you to observe something. So why wasn't I screaming in pain when the red laser pointer hit my hand? Well, the simple answer is because it wasn't absorbed and turned into heat. Let me explain. If I take the red laser pointer and put it up to my hand, you can see that a lot of the energy is still the red laser light and is simply diffused and scattered within my skin. So very little of it is actually converted into harmful heat energy. Let's take a look at the infrared laser. It's quite a powerful laser, but if I put it up to my hand, You can also see that the majority of the energy inside of the laser beam is not absorbed and converted over to heat, but instead it's diffused within inside of my skin. Why is this important? Well, you're about to find out. Now let's talk about the actual dangers of laser light. And yes, infrared laser energy can be rather hazardous, but these hazards normally come from things like modifying a green laser pointer to be just infrared, in which case the energy levels can be anywhere from 100 milliwatts to 500 milliwatts or more. Other hazards include things like infrared cutting lasers for doing engraving or cutting of materials, and working inside of a DPSS laser head, where the infrared energies can exceed 20 watts easily, which is a lot of laser energy. And the biggest danger in infrared is the lack of blink reflex. Since you can't see it, you can't respond to it, and if you can't respond to it, it just slowly cooks your eyes. Let's check out another real danger, and that comes in the form of these cheap 405 nanometer eBay laser pointers, which are listed as 5 milliwatts. But how much power is coming out of these in reality? This one's doing 60 milliwatts. And other people have said that they've seen these all the way up to 100 milliwatts or more. Well, why is this dangerous? The first reason is that your eyes can't pick up the 405 nanometer laser light as well as it can pick up things like red laser light and especially green laser light. But the other problem is that this frequency is also really easily absorbed by the cells inside of your skin or retinas and is very efficiently converted over into heat. So, how well do the cells in your body actually take and convert over the 405 nanometer laser light wavelength into heat? Well, for that demonstration, I have a fairly high-powered 405 nanometer laser pointer, and I have my hand. And I'm sure this is a demonstration of which you're looking forward to a lot more than I am. Oh, that stings, and I'm certain that pretty much gets the message across. There are many people who enjoy using laser technologies, and for those of you who follow my content, you definitely know that I'm a fan of the technologies myself. However, what I'm not a fan of is when companies produce laser pointers and label them as 5 milliwatts and they exceed this output power. And this is for two main reasons. The first reason is that when people get their first experience with laser technologies, it's often through the purchase of a cheap laser pointer, and when they buy one they think it's 5 milliwatts and isn't, they're just exposing themselves to unforeseen risks. The second reason is that there are a lot of countries that have policies on the amount of output power that a laser pointer can have, and when these laser pointers test above the 5 milliwatt or 1 milliwatt range, a lot of these countries will impose policies on importing laser pointers. And that means that a lot of people don't get to experience the technology and learn about it. Now you might be wondering, is my laser pointer safe? Well, this can be very hard to determine without a proper laser power meter. However, I have devised a really simple test that will hopefully help you determine this on your own. All you'll need is one of these really thin black shopping bags, and we'll use this as our cheapo laser power meter. First I'll start off with the grass green laser pointer, and this is under 10 milliwatts. And I'll just hold this up to the front of the laser aperture, and we'll see what happens. And there is no change at all. Now let's check out the cheap 405 nanometer violet laser pointer. And you can see that there's a little hole in the black material. And for reference, let's check out the output power of one of the modified green laser pointers that now just puts out the infrared laser light. Yeah, you definitely don't want that in your eyes. So, all in all, there really is no such thing as a perfectly safe laser pointer. So the first thing to keep in mind is always use precautions when handling and working with laser technologies. Now, let's get into the Shunt Mod. Let's take apart one of these really cheap retinal removers, and it's a pretty simple task to do, much easier than the green laser pointers. First thing is to remove the front end cap that protects the lens and other stuff on the inside, and this can be pretty easily accomplished by hand. Otherwise, you're going to wrap some tape around the front, put it into a vise if you want to protect that front piece, and then we're going to take it apart like this, and you'll see that there's a little round rubber foam piece on the inside. Simply use a small flathead screwdriver to take that out. Now you're going to want a piece like this, and you can use a tube that's cut like that, but the reason why there's a gap cut in there is because you have to make room for the button as you push this forward. Unlike a green laser pointer where I extract it from the front, we're going to end up pushing it out from the back. And the way this works is like this. So this piece goes around the circuit board, and it presses up against the plastic piece right here, which presses up against the front area. So, open the vise to the proper size. And we'll put this piece in the back, just like this. You're ready to press it out. Now at one point the button is going to slip down, and that can get a little tricky, so when we get to that point, I'll show you what to do. So you see how it starts to slip down right there. Now when the button is in this position, keep going just a little bit, and then you're going to take out that little press piece from the back and remove the button. It's going to get caught up on the spring, if you see in the inside. You're going to have to kind of lift it up over the spring, and it should come out pretty easily. With the button removed, you can now continue to press it out. And by this point it should be easy enough to press out by hand. You know what the magic word should be. There we go. Here's the laser module assembly, of which you'll typically find inside of a cheap 405nm laser pointer, and its construction is pretty simple. On the front here, you'll have the laser diode host and focusing assembly. You can see on the back where the laser diode is pressed in, and on the front where the collimating lens is just threaded to a certain distance away from the laser diode for optimal focus. The laser diode itself is connected to the laser diode driver, And the architecture that this laser diode driver uses is what's known as an asynchronous boost. So this laser driver actually steps up the voltage. Now how does this work? So for example, if you wanted on the laser diode about 7 volts at 100 milliamps, and you had a voltage supply going in at 3.5 volts, it would take about 200 milliamps from the supply voltage at 3.5 volts, and it would use the MOSFET inside of this little 6-pin IC to pulse the inductor. Now, unlike a transformer, the inductor only has one turn of wire on there and relies on the collapsing magnetic field to produce a higher voltage. The voltage coming off the inductor is then rectified by this little diode right here, and it's reversed. So if you put in voltage one way, the magnetic field collapses and you'll get a reverse voltage out. Now the voltage coming out of the inductor relies on two things. Firstly, it relies on the load being driven, and in this case, because it's a regulated boost drive, the current sense resistor right here, which is the important part of this video. But these are incredibly handy little drivers to have around. The amount of voltage that these little boost drives are capable of producing might be higher than you would suspect. To show you this, I have soldered on 2 wires from the output of the boost drive, and I have these wires connected up to my multimeter. Now because there's no load on the output of the boost drive, there's no current for it to regulate, so you'll see the full voltage output of the boost drive just on its own. And as you can see, the voltage is about 25 volts. Now one thing to note is even after the boost drive is turned off, there's still a bit of voltage present, and it's best to short out the output just to make sure that there's no voltage stored up in the little capacitor that's located right here on the boost drive. These are commonly used to light up the backlight LEDs on portable LCD devices because they can produce quite a bit of voltage and run all the LEDs that are in series. To help you understand how this little boost drive works, I've connected up a string of 5 1-watt LED beads, and I'll be showing you the voltage that goes through the LEDs. So how does this little boost drive seem to magically know what voltage should go to the LEDs? Well, in truth, it doesn't. It only knows the current. Now let's measure the amperage going through the LEDs, and to do this I have my multimeter in series with the LEDs and the driver, and I have it set to measure DC current. So here we have about 100 milliamps, and we'll see the same current as I work my way down the string of LEDs until we get to the last one. Now we have a different number, and that's because whenever the boost driver is putting out less voltage than the input voltage, it doesn't regulate the amount of current very stable at all. And I'll talk more about this later on in the video. But first, how to adjust the current that the little boost driver is putting out by changing the value of the shunt resistor. Now it's time to put on your thinking caps because it's going to get a little bit more complicated. So I have 2 more wires soldered onto the laser diode driver, and each one of these wires is on each side of the shunt resistor, which is marked 3R3. I have my meter in ohms, and it's showing me 3.3 ohms, which is what it should be showing. So the next thing I want to do is I want to put the meter into the volts range, and I want to see the volts that are going across the shunt resistor. So if I turn it on, it says about 0.3 volts. So the way this circuit works is that the first couple of pulses that are sent to the inductor get sent through, and it builds up the current until it reaches the 0.3 volt range on the shunt resistor, and then holds it at that point. So for example, if I throw another resistor in parallel with the resistor that's being used for a shunt, this one's a 2.7 ohm, it'll still hold at that same 0.3 volt range. However, because it takes more current to reach that range, the LEDs will be brighter. So with that resistor off, it's dim, and as soon as I attach it, it gets brighter. Knowing the voltage across your shunt resistor is very important, because this is where the important mathematics come from. We already know that there's about 90 milliamps coming out, and we can see that by doing the Ohm's law calculations. So we start with the voltage, 0.3 volts, and we divide that by the resistance, 3.3, and we get 0.090, or 90 milliamps. I'm going to clear that. Now let's test out the resistance with this added shunt onto it. That's about 1.4 ohms. So let me go ahead and connect that up to these wires, and then we'll use that same calculation to see what we should be producing as far as current, and verify that by turning the driver on. So that's in place. And we're going to connect the meter up. And let's do some calculations. So I'm going to start off with the same 0.3 volts. And I'm going to divide that by 1.4. And it shows we should be getting about 200 milliamps out of the driver. Is that what we're getting? I'm going to put the meter into the DC current range and test out the current. And right there, we're getting about 200 milliamps. Now, if you're wondering how to find the proper resistor for the current you want, you can also do the reverse and start with the voltage once again. So say for example you want 500 milliamps, let's say 50 milliamps. So you want 50 milliamps coming out, we'll do 0.3 divide by 0.05 and equals 6 ohms. So for 50 milliamps output, you would need a 6 ohm shunt resistor. Now let's test out the hypothesis of using a 6 ohm shunt resistor to get about 50 milliamps. And I have two of the 3.3 ohm shunt resistors in series, giving me 6.6 ohms as seen on the meter. And if I go to test out the DC voltage across the shunt resistors, we should get about the same 0.3 volts. Let's now see the current that we're getting through this. So disconnect that. And connect up those to the meter and put it on DC current. Are we getting about 50 milliamps? Yep, we sure are. Here on this 405 nanometer laser pointer module, I've done the same thing, and I've taken two of those 3.3 ohm resistors and put them in series to give me a resistor shunt value of 6.6 ohms. Now the question is this safer on the eyes? Well, let's find out. Looks to be under 10 milliwatts. Let's now perform the black bag test. I'll put that in there so I have something to put the bag over. Gonna grab the bag, hold that over like this, and we'll get a good view of those results. Yep, looks to be pretty safe to me. Now I know there are those of you who might be wondering what the full capabilities of these little boost drivers might be. So to test that, I have these two wires, so I can put another resistor in parallel with the shunt resistor that's already there. Right now it's a stock 3.3 ohm resistor. I have an M140A type, which is a 1 watt capable 445 nanometer blue laser diode. And I have my multimeter set to measure DC current. So we should be getting the 90 milliamps right now, which is barely nothing to get the M140A type running. Let's see how it runs with the 2.7 ohm resistor, which should give us the same 200 milliamps that we saw before. And it does, and gives us about 80 milliwatts. Let's try a 1.2 ohm resistor. That might bring us to around 300 milliamps. And we're getting about 300 milliwatts out at 400 milliamps about. Let's try a 1 ohm resistor. About 430 milliwatts and half an amp. Not too bad. Doing pretty well. Let's bring it down all the way to 0.5 ohms. Hey, we're getting about 700 milliwatts out and about 700 milliamps going in, which is pretty good. Oh. Well, it looks like the chip is getting pretty warm. The thermal protection has started to kick in, and that's why it's blinking. Looks like I'm going to have to throw a heatsink on there. I have placed a little heatsink on the IC here, and I still have the 0.5 ohm resistor in parallel with the 3.3 ohm resistor, and it's time to continue testing. So let's connect it up and see how it runs. How about 700 milliwatts at 700 milliamps? Let's drop the resistance down even lower with a 0.3 ohm resistor, and theoretically this should give us about 1 amp output. But about the same, 800 milliamps, and about the same 700 milliwatts of output power. Let's really drop it. I have a 0.8 ohm resistor here, and I'm just going to put this in parallel with the two resistors that are already on there, and we'll see what it does. Yep, it's holding about the same. It looks to be 800 milliamps is its upper range. That's about as much power as you can push through this little boost driver. That's not bad. Not that bad at all. Earlier in the video I showed you a string of 1 watt white LED beads and how all of them got 90 milliamps, except for when there was only one LED bead connected up to the boost laser driver, and it got more current. And this happens when the output voltage of the laser driver is lower than the input voltage of the laser driver. So here I have a stock setup, so the same 3.3 ohm resistor and 405 nanometer violet laser diode. Now if I press the button, we'll get the expected 90 milliamps coming out. Now these laser drivers are excellent if you're driving a higher voltage laser diode, like the direct diode greens, the cyans, blues, or violets. However, they don't work very well for the DPSS 532 nanometer greens, red laser diodes, or infrared laser diodes. So, what exactly happens when you connect a lower voltage laser diode to one of these boost drivers? Well, let's find out. So I'll be taking out this violet laser diode and placing a red laser diode onto the boost driver. Now let's check the current going to that laser diode. It's 180 milliamps. That's well above what it should be regulating. Now, let's check out the voltage going across the shunt resistor. Well, that's not right. Let's try a DPSS green laser diode assembly and see what that says. And about 300 milliamps going to that. Also not 90 milliamps. Let's check the shunt voltage once again. It's also an incorrect voltage. Now I have one of the 1 watt white LED beads connected up to the boost driver, and that's going to be powered off the adjustable power supply here. I also have my meter, once again, measuring DC current, and the LED takes about 3.3 volts at 90 milliamps. So it should regulate 90 milliamps going to the LED, and when we exceed 3.3 volts going into the boost drive, we should see the current start to climb because it's failing to regulate properly. So let's check out and see if that happens. As expected, we have 90 milliamps, and I'm going to turn up the voltage. So now we're at 3.5 volts going in, and at this point we should start to see the current climb. And there it goes. This is what's causing the current to climb on the lower voltage laser diodes, and which is why you use a different driver to power them. Well, I hope you enjoyed this video and learned quite a bit, and as always, Stay tuned for more.